Okay, guys, let's talk polar. Polar is a completely different system, just like parametric. We've been working with parametric for a few days. Now we're going to talk about this one. Basically, what it's based on is this: a whole new way to locate a point in a plane, in a two-dimensional plane. What you've learned how to do for several years now is if you want to find any point in a plane, you describe that point by how far it is to the left or right of the origin, which we call x, and how far it is up or down from the origin, which we call y. So, for example, we could say that this polar bear is located at 4, 3, for example, which means 4 units right and 3 units up. And there is no place in 2 dimensions that you cannot find using that system. Polar is just another way to locate the same point, any point in the system. Instead of saying, okay, if you want to find the polar bear, go 4 steps right and 3 steps up. Instead, we first point in the correct direction and say, okay, if you want to get to the polar bear, starting with 0 degrees, which is the same as our unit circle setup, starting with 0 degrees, turn yourself positive 45 degrees and look that way, and then step from there 1, 2, 3, 4 units. So an old point used to be xy. A new point is going to look like r theta. All right, so we could describe the location of this polar bear as 4 steps at 45 degrees, or 4 steps at pi over 4 radians. All right, so there's that's really the basis of what we're going to do for the next 3 or 4 videos. It's just about a new way to find a point. Um, One interesting thing about polar is there are a lot of ways to describe that same point for pi over 4. That's one way to do it. Another way would be, what if we went around the whole circle once and then got back to pi over 4? You've done stuff like this with your unit circle work in the past. One way to get to the polar bear would be starting at 0 degrees, rotate 2 pi and additional pi over 4, and then go 4 steps. So 4 steps at an angle of, let's see, 2 pi plus pi over 4 would be 9 pi over 4. And if you can say it 4 pi over 4, there's not really, any reason to do 4 9 pi over 4 other than just to know that they exist. Um, Another possible way would be, what if we went negative, we faced in a direction negative 3 pi over 4. So we're pointing actually this way. This is our direction. If you want to walk the other way, then that's negative 4. So point the other way and take negative 4 steps. You still 1, 2, 3, 4 end up back at the polar bear. So there are a lot of varieties in naming a point with polar, whereas in XY you just had one option. All right, so next, how do we convert this point from one to the other? All right, I've got a polar bear sitting here at 4 units out at an angle of pi over 4. How could I know, like, if, how could I know the x, y coordinates? And this is just some basic trick. Converting from polar to rectangular and vice versa. Set up a little triangle, and let's first start with um, polar to rectangular. All right, I tell you the polar bear is at 4 pi over 4. How do I know how far left or right or how far up or down the polar bear is? Okay, so how far is this and how far is this? That's the question. And again, this is not anything too difficult. for this specific, let me, before I get into this too far, let me generalize because I don't want to use 4 and pi over 4 and then have to get to the formula. Let me call that radius and that theta. All right, so again, those of you that have done physics, you've done this exact same setup hundreds of times. Even if not, whatever trig you know, it shouldn't be too hard to figure out what x is. Okay, set up a trig ratio. X is my adjacent side to my angle theta. So if cosine of theta equals x over r, then r cosine theta would have to equal x. So if I give you a polar setup, then changing it to x is no big deal. Let's just get those summed up. X is r cosine theta, y is r sine theta. So I'm kind of all over the place with my notes today, but just make sure you have those formulas written down to translate between polar and rectangular. All right, what if I knew the other way? What if I knew x and y and I wanted to know r? So this we'll call rectangular to polar. If you know x and y, then finding r is just a basic Pythagorean theorem. R squared equals x squared plus y squared. So square your two parts, add them together in square root, and you get r. And then how do you know this angle? If that's in question, the ratio would be tangent of theta equals y over x. So theta is going to equal the inverse tangent of y over x. And that will, those two sets of formulas in red will help you translate between rectangular and polar whenever you need to. So let's talk about polar graphs for a minute. We saw with parametrics that parametric equations allowed us to create very interesting shapes and even graphs as cool as the spiral graphs and stuff like that. Polars, similar. They'll let you create shapes that you've never been able to graph before. You could, so it also will let you do basic graphs too. For example, if you just had a simple equation like r equals 3. This is sort of like if I graphed x equals 3, that's saying no matter what y is, x is 1, 2, 3, and it gives us a vertical line. If I say r equals 3, that's saying no matter what theta is, no matter what my angle is, the radius is always 3, or my distance from the origin is always 3. So that's going to give me a circle. All right, that's the graph of r equals 3. The graph of theta equals pi. That's saying no matter how far from the origin we get, my direction that I'm pointing is always pi. So pi is over here, right? And it would extend the other way too. So all points where the angle is pi look like that. If you had a different angle, theta equals pi over 3. You would go to 1/3 pi, which is, I'm not sure if it's exactly this line or not, but here's a graph of theta equals pi over 3, like that. So you have to kind of think of the graphs differently. It's interesting to me that in x, y, and rectangular coordinates, the equation of a circle is pretty, a circle with radius 3 is, x squared plus y squared equals 9, which is a fairly complicated thing because we're trying to get a circle into a rectangular situation. Well, polar is like circular stuff is in its own world. It's very simple and brief. So that's why the equation for the circle in polar is so basic, and in rectangular it's so complicated. So these aren't the graphs we're really interested in. I'm interested in the cool graphs. So the best way to do those, in my opinion, is to play around with your calculator and just try some stuff. Back to mode, where we've just learned how to get into parametric. If you'll notice, POL is polar. When you change to that mode, now your y equals is suddenly r equals. So our functions are now, we used to have y in terms of x, or we could have written it like f of x in terms of x. Well, now we are in polar, so it's r in terms of theta, or f of theta in terms of theta. R and f of theta are the same, just like y and f of x are the same. So that little side note aside, talk about graphs. These let you create some really interesting graphs, and some of them are like famous ones that have their own names and stuff. How about r equals cosine of 2/3 theta? Cosine of 2/3 theta. Notice how your xt button now gives you a theta. And we had to adjust our t's when we were doing parametrics. We might have to adjust our theta on this graph and see to make sure it graphs the whole thing. I think my zoom is too far zoomed out, so let's do a zoom 6, which gives me back to 10 in all directions. And that's still too small. You can cosine is at its biggest 1, so let's see. I'll go in at least once. All right, so it looks like I've got something forming, but I might not have the whole thing. So in your window, it gives me my theta min and my theta max. Maybe I need to go past 2 pi, so I'm going to try 6 pi, see what I get. And there you go. So you get this interesting graph that you've definitely never been able to graph in just x's and y's. I could probably zoom a little bit more if I do -1.5 to 1.5 in both directions. Get a little bit better idea. But there's an example of a cool polar graph that is generated from a fairly simple equation. So if we're going to graph stuff, that's pretty much the way it's going to get graphed. I want to show you really quickly one more thing. I'm going to pause and get some writing out of the way so I can get this done quickly so this video doesn't go too long. So pause. Okay, so if you will, pause and write this down, and I can just talk through it, and then this won't last too long. I have to give you something else or we won't have any problems to do in class because we haven't really done anything you can answer questions about. So how do you get the slope of a polar? It's, first of all, up here, this is like y equals f of x, but it's r equals f of theta, just new variables. I told you on our front page, when you convert from polar to rectangular, x was our cosine and y was our sine. What that also does is it gives us a parametric form of our polar equation, where x and y are both defined separately in terms of theta. Now, using number 1 and number 2, if you substitute in f of theta in for r, you get 3, which is x and y in terms of theta only. Now, based on that and what you know about parametric derivatives, the derivative of y with respect to x here is equal to the y derivative over the x derivative. That's parametric that you've been working on. And then we just need to take the derivative of y. Here's y, and its derivative is based on the product rule. First times derivative of the second plus second times the derivative of the first. So here's the first, here's the derivative of sine, here's first and here's second. First times the derivative of the second plus the second, which is sine, times the derivative of the first, which is f prime. And we do the derivative of x similarly. So we can talk about this more face to face. I just wanted you to have that formula ready to use. And it looks really bad, but it's not going to be that bad in use. Okay, so we will call that a day on Polar Day 1. And I will see you here, Young out.